recording.
I'm hitting the record button. All right, so this time, here we go, class session take 2 because I'm stupid. All right, so our goal today is to follow up on what we did on Friday. In Friday, we learned the Coulomb force law. And let me go ahead and switch to the share screen camera. I'm going to try to do this pretty quickly because when I did this the first time, I forgot to hit record. All right, so the Cliff Notes version. So we learned the Coulomb force law last week. This says that this is how much force gets exerted by a point charge when it's near another point charge, right? K is the Coulomb constant, Q1 and Q2 are the charges, and R is the distance from one charge to the other. So if I had a positive charge here and a positive charge there, R would be that distance there. And this represents how much force those two charges exert on each other. Now, what we haven't really addressed is why are they able to exert a force on each other at all, right? Normally, for most forces, the two objects in question have to be touching, right? That's the way that the force was mitigated from one to the other. But here, these two charges, they're not touching at all, and yet somehow they're still able to exert a force on each other. The way that we're going to kind of resolve that question is we're going to suggest that there's the existence of something called an electric field, right? The electric field is a disturbance that's caused by charges that creates the Coulomb force. And the analogy that I like to think of when I'm imagining how this electric field works is I think of like a waterbed. Now, imagine here's a waterbed, and there's nothing sitting on the waterbed, so the surface of that waterbed is completely flat. Now, if I take something small, like say a tennis ball, I put a tennis ball on the waterbed, it creates a little kind of divot on the waterbed, but still the waterbed is mostly flat. However, if I add a second larger object to that same waterbed, like imagine this is a bowling ball. Now what's going to happen is that bowling ball is going to create a much bigger divot, a weird sort of curvature to the surface of that bed. And what's going to happen is because the bowling ball is curving the bed, well, the tennis ball over here is going to tend to roll down the surface of the bed and towards the bowling ball. It's almost as if the tennis ball is feeling a force attracting it to the bowling ball. Now, we know that it's not really feeling a force from the bowling ball because the bowling ball is not touching it. Instead, what's happening is the bowling ball disturbs the bed, and the bed interacts with the tennis ball, and that's how that force propagates to the tennis ball. That's the way we'll think about the electric field. We're going to imagine that these positive charges create this weird disturbance everywhere in space around it, right? The mere fact that it exists causes a disturbance. And what's going to happen is this other charge, it may not be touching this charge, but it is touching the disturbance created by the other charge. And that's why it's able to feel this Coulomb force. That's the idea of the electric field. That's how we're going to imagine that these charges are exerting forces on other charges. All right. Now, here's why this concept is useful to us, right? In order for me to talk about the Coulomb force, I got to specify both charge 1 and charge 2. I got to know both Q's to make that a useful thing to use. However, if I were to just have a bowling ball sitting on a bed, right, the bed is going to be all weird and curvy, even if there's no tennis balls around to feel the force, right? That disturbance exists whether or not there's anything else on the bed to get pushed around by it. And so when we talk about the electric field, effectively what we're doing is we're talking about the curvature or the weird disturbance created by just one charge. I only have to specify one charge in order for that to happen. And so that is how we're going to come up with the definition of the electric field. All right, so the electric field is going to be defined as the ratio of how much force you feel divided by how much charge is feeling that force. So what's going to happen is, since F is something like this, and Q is one of these two charges, it doesn't really matter which. Well, what's going to happen is, if I take this and divide it by one of those Q's, whichever Q I'm dividing by will cancel. And I'm only going to be left with a single Q. So since there's only one Q left at this point, we're just going to drop the indices and just call it Q instead of Q1 or Q2 or whatever. And so this is the expression for the electric field of a point charge. It's KQ over R squared. Okay. If I had something more complicated than a point charge, I'd have a more complicated formula, but for point charges, that's it. Now, this idea of a field is important because a field is actually a math term, right? It comes from the idea of a vector field. And a vector field is a vector whose magnitude and direction is different at different locations in space. We've already learned about one field last semester when we talked about gravity, right? Gravity is the result of a gravitational field. And what's going to happen is the magnitude and the direction of gravity depends on where you look. If this is the Earth and this is the guy standing on the surface of the Earth, obviously not to scale, this guy feels a force of gravity pointing straight down towards the center of the Earth. But this dude over here in China, he feels a force in the exact opposite direction, right? This guy over here in, I don't know, Ecuador or whatever, he feels a force in yet another direction. This guy over here in the Dragon space capsule, he feels a force in a yet still other direction. And because he's further from the Earth, the magnitude of that arrow is even smaller. So depending on where you look, you get a different magnitude and a different direction for the force of gravity. And we're going to do that same process for the electric field. This formula, however, only tells me the magnitude part. It tells me the number for the strength of the gravitational field, or the electric field. It doesn't show me the direction. So to get the direction, let's imagine this example. Here's a little positive charge. And for convenience sake, I'm going to say this positive charge is 1 nanocoulomb. Now, the reason I'm using 1 nanocoulomb is because 1 nanocoulomb is 1 times 10 to the negative 9th coulombs. And if I'm trying to evaluate the electric field, I'm going to be taking K, which is 8.99. I'm going to round up to 9 to make it easier, times 10 to the positive 9th. If I take 9 times 10 to the positive 9th times 1 times 10 to the negative 9th, I'm going to get in the numerator of this fraction 1, or 9, excuse me. Yeah. So I have 9 up top no matter what, and R is the distance from where the charge is to wherever it is that I'm looking. And I can look at different locations and find the electric field. If I look 1 meter to the right, then what's going to happen is I'm going to have 9 divided by 1 squared, so 9 newtons per coulomb. But I need to know the direction for the electric field there. And to get the direction, the rule is this, right? You look at the spot that you're trying to find the electric field, and you imagine putting a positive charge at that location. The electric field points in whatever direction that imaginary positive charge would get pushed. So if I imagine putting a positive charge here, it would be repelled from this positive charge there, and the force would be to the right. If I were to put that positive charge here, also 1 meter away, the field would still be 9 newtons per coulomb, but it would be in this direction. And at each of these locations, I'm getting the same size field, but they're always pointing directly away from that positive charge. Now, if I went, say, 3 meters out, then what's going to happen is out here, this would be just 1 Newton per coulomb. It would be a lot smaller, but the direction would still be away. So what's going to happen is we can see that for a positive point charge, the electric field always points radially away no matter where you look. Boom, super easy. So from that, let's do an example. And of course, because we can't just simply have single point charges all the time, we're going to have something more complicated than that. Let's do 2. So the good news for us is that if I have multiple point charges, here's a positive 50 and a negative 10. If I want to find the electric field at some location, each one of these charges is going to be creating its own electric field. The good news for us is that all electric fields, like any vectors, obey something called the principle of superposition, which is a fancy schmancy math way of saying that electric fields add like vectors. Just find each one individually and add them up. So for this problem that we worked out originally, I said I want to look right here in the center, halfway between these two point charges, and find the electric field. Now, what's going to happen is I'm going to get 2 electric fields, one from the positive charge. So to find its electric field, I'm going to ignore this guy for a second and only worry about this guy. I imagine putting a positive charge here, and I ask myself, what direction would that positive charge get pushed by this guy? And the answer is it'd be pushed away from it. So E1 is to the right. How big is E1? Well, I do K Q1 over R1 squared. Well, K is 8.99 times 10 to the 9th. Q1 is 50 microcoulomb, so 50 times 10 to the minus 6. And R1 is going to be the distance from here to here, which is not the entire 0.2 or 20 centimeters. It's half of that, so 0.1 squared. So you crunch all those numbers, and that's what I get for E1.
Dr. Fleming?
Yes, ma'am.
I had got that, but times the power of 5.
It's possible that I screwed up. Let me double check. It's also possible you didn't square the denominator. Nope, you forgot to divide by the 0.1 squared.
Definitely forgot to divide by the 0.8. Okay.
Yep.
Let's see. Let's go back.
Yeah, the fact that you were off by exactly a factor of 10,000 is how I knew.
Okay.
Or by not 10,000, a factor of 100. All right. So this is the electric field for the positive point charge. For this point charge, we'll do the same process. Now, first, let's think about the direction. This is a negative charge, right? If I put a positive charge here, that positive charge would be attracted to that negative charge. So it would point also to the right. That's cool. Even though these two charges have opposite signs, their electric fields both point in the exact same direction. So I'll call that the positive direction, and these will both be in the positive direction. When I go to evaluate the size of E2, it's going to be K times Q2. Notice I'm not putting a negative sign in here because I'm finding the magnitude of E, divided by the distance, which is still 0.1. So that's going to give me my total electric field when I crunch those numbers. And since I'm adding 2 vectors that are in the same direction, it's just like regular addition. So this plus this equals this. Yay! All right, so super easy. We can do this in our sleep. How are we feeling?
Pretty confident, but I'm trying to get my E total first before I move on.
All right, take a stab at that. All right. So what we're going to do next is we're going to make it more complicated. So in this picture right here, obviously, if I look right here, the electric field is not 0. It's actually quite large. Is there any location that I could look and get an electric field of 0?
You said, was there anywhere you can look to get an electric field of 0?
Yeah. If I look someplace else, is it possible that the electric field ends up being 0?
Possibly.
All right. Where would I look? You know, I'm not going to leave it at that, right?
I'd say about.
I'm just redrawing it without all the clutter. So we looked right here, and we got an electric field of like 5.39 times 10 to the 7th. That's like 53 million. That's how big the electric field was right there. So clearly that's not 0. Is there a place where the total electric field would equal 0?
Closer to the negative number.
Okay. Well, since the electric field goes as kq over r squared, if you get further away, that's going to make the field weaker. And if you get closer, that's going to make the field stronger. But the problem is, if I look, let's say like right here, I'm further away from this, it's going to have a smaller electric field, but it's still going to be to the right.
Yeah.
This is going to be a bigger electric field. It's going to be still to the right, but that's still not going to equal 0, right?
No.
Because I'm adding 2 electric fields that point to the right. So where could it possibly be? Where could I look where the 2 electric fields could cancel out?
So since they both go to the right, you need one to go negative.
Yeah, I need to look in another location where one of the electric fields would point to the left and the other one will point to the right, or one would be up and the other would be down.
I'm kind of lost.
What if I look over here?
Yeah.
Right. If I look over here, what direction is the electric field from this guy?
To the right.
That's correct. So E1 would be to the right. Now, what about this guy?
To the left.
There we go. So what's going to happen is if I look not in between them, because in between them, they're going to both always point to the right. That's never going to work. If I look on this side over here, if I pick the spot just right, this guy is going to be to the right. This guy is going to be left. If I pick the spot just perfectly, maybe they're opposite directions but equal size, they'll cancel out. Now, what about over here? Could that work?
So E1 or E3?
Well,
or let's
could
do
I get
E1.
0 if I look over here?
E1 would be pointing towards the left.
Correct.
No, the left.
All right. And then this guy over here would point
to the right.
Aha. So in principle, this could work because they'll be in opposite directions on that side as well. Now, in practice, one of those will work and the other one will not. Any idea which one's going to definitely not work?
Can you repeat that?
So at somewhere over here, if I go to the right of this negative charge, there's going to be a place where E1's one direction and E2 is the other direction. If I look to the left of this charge, there's a place where E1 is in one direction and E2 is the other direction. So in principle, I can imagine these things canceling out in either of these two locations. One of them, however, isn't going to work.
And
if you don't see it, don't worry about it. We'll figure it out here in a minute.
Okay.
But one of them is stupid, and we'll see why in a minute. So let's pick this spot over here. Let's do this one first. All right. Now, in order for this to happen, E1 minus E2, because this one's in the positive direction, this one's in the negative direction, has to add up to 0. So let's go E1 minus E2 equals 0. We're going to require that to be true. And then we're going to see where that will happen. Does that make sense?
Yes.
So how will I find E1? E1 is going to be the distance from this charge to this charge, right? And remember, this distance in the previous problem was 20 centimeters, which is the same as 0.2 meters. So if I'm solving this, if E1 minus E2 equals 0, that means that E1 has to equal E2, right? They have to have the same magnitudes.
Mm-hmm.
Now, E1 is K times Q1 divided by R1 squared. E2 is going to be K times Q2 divided by R2 squared. And what I'm doing is I'm trying to figure out where to look. So I'm basically solving for R's, right? I want to know like where on this thing, what position to put my electric field in. If I'm solving this expression here, though, the first thing I notice is that there's K's on both sides, which means they're going to cancel.
Okay.
So the trick is going to be figuring out what to do with R. So what does R represent again?
The distance between the points.
Aha. So on my picture, R1 is going to be the distance from this guy all the way to there. So R1 is however far that is, right?
Mm-hmm.
But R2 is from this guy to wherever that is. R2 is that way smaller distance.
Well, we're R2.
What's that?
I was saying where was R2, but it's up there at the top. I see it.
Yeah. So you see where I'm going?
Mm-hmm.
Now, one thing that I notice is that R1 and R2 are definitely different, right? R1 is a way bigger number than R2.
Mm-hmm.
And right now, I don't have a number for either one of them. So I can't necessarily solve for either of those two things.
Okay.
So what I need to do is to reduce the number of unknowns in my equation, right? I have one equation with two unknowns. In order to make that solvable, I need another equation. So could I find a second equation that I could use in tandem with this equation involving R1 and R2? Are R1 and R2 related to each other in any other way?
They equal each other.
No. R1 is this big distance and R2 is this little distance. They are definitely not the same.
Okay, no, they're not the same. You said, what was the question?
I'm trying to relate R1 and R2 to each other. I need a second equation that involves R1 and R2. Just to give you a hint, this is not anything complicated. It's not something you have to look up. It's actually something that you could have asked your 5-year-old nephew, and he could answer it. Maybe not 5-year-old, but maybe like 8.
Add them? No, they don't add together.
Something adds together.
I'm not for certain.
R1 is this, right?
Uh-huh.
But wait a second. This is the same as this and also this.
Yeah.
So this is 0.2, and that's whatever R2 is. So basically what we're saying is that 0.2 plus R2 has to be the same as R1. That's an equation.
Okay.
So R1 has to equal R2 plus an extra 0.2.
So R1 R2 plus 0.2.
So you see how we got that?
Yes.
Now, if R1 equals all this garbage, all I got to do is plug this in for R1 over there. So now I've got Q1 over R2 plus 0.2 squared equals Q2 over R2 squared.
Hold
Okay.
on.
That helps us a lot because now this only has one variable in it. Q1 and Q2 are numbers.
Yeah.
So all I've got to do now is just solve for R2. So how do I solve for R2?
Okay, give me 1 second because I was paying attention. So that's this under Q2 is R2 squared. Yeah. Okay, so what would this be? Let's see. What would you ask after that? I was writing the equation. So how do we solve for
I'm trying to solve for R2. I need to get R2 by itself.
multiply by Q2,
Well,
right?
not quite. So what I'm looking at here is a proportion. Right? I have a fraction equals a fraction. And when you learned how to solve proportions back in the day, whenever you guys took algebra, the way you deal with proportions is cross multiply.
Yeah.
Like this times this and this times this. What I'm doing basically is I'm getting rid of all the fractions because fractions are cramping my style. So over here, I'm going to have Q1 times R2 squared. And on the other side, I'm going to have Q2 times R2 plus 0.2 quantity squared. So at least I don't have any more annoying fractions. That's a step in the right direction.
Yes.
Right. So now what I'm going to have to do is I got R2s over here and I got R2s over here. So what I need to do now is get all the R2s together. Let's FOIL this out, distribute that Q2 through it, and then get all my like terms collected.
Okay.
Right. So first thing I'm going to do, I'm just going to rewrite. So I have Q1 R2 squared equals Q2 R2 plus 0.2 quantity squared. All right. So the first thing I'm going to do, let's get this out of the glare, is let's FOIL this out. So when I FOIL that out, I'm going to have the first one squared, so R2 squared, plus it'll be 2 times this. So that's 0.4 times R2 not squared, plus 0.2 squared, which is 0.04. Do you see how I did that?
No.
All right. This is flashback to like way back. If you have A plus B quantity squared, that equals A squared plus 2AB plus B squared. Remember that?
Yeah.
You learned it back in algebra like a million zillion years ago.
Yeah.
Yeah. And the reason is because I had to multiply like A times A, and that gave me A squared. I had to multiply B times B, that gave me B squared. But then I have those cross terms when you're doing the FOIL thing. So you'll have, if you have A plus B, what's going to happen is you're going to have one term where you multiply this guy times this guy. That's going to give you A times B. Then you have another one where you're multiplying this guy times this guy. That's going to give you A times B. And that's why you have 2AB.
Okay.
So
R2 squared equals Q2
just a little bit of algebra.
squared.
And I can take Q2 and just now distribute it through each of these. So now I've got Q1 R2 squared equals Q2 R2 squared plus 0.4 Q2R2 plus 0.04 Q2. So far, so good?
Yeah. Yeah.
All right. One last step.
Okay.
I got R2 here and R2 squared here and R2 squared here. Let's get all the R2s together. Let's just subtract this from both sides. So I've got 0 equals, and I'm going to have Q2 minus Q1.
Whoa.
And that seems all complicated and everything. Except, wait a second. This is a number. This is a number. This is a number. They're all numbers. And what am I solving for? This. So I have an equation with some number times my variable squared plus some different number times my variable not squared plus some different number that's not times my variable at all. What kind of equation is this?
Hmm. uh, algebra. No.
Looking for a very specific kind of equation that you learned about in algebra class a million zillion years ago, where you've got something x squared plus something x plus something equals 0.
Yeah.
The word you're looking for is quadratic. This is a quadratic equation.
That is something is being square rooted in that stuff like that.
No. Quadratic formula or quadratic equations are of the form ax squared plus bx plus c equals 0. And if that's the case, x has to equal negative b plus or minus the square root of b squared minus 4ac
Over 2a.
right? So for this problem, what is a? It's the stuff that's times the x squared. What is b? It's that. What is c? It is that.
Mm-hmm. Okay.
So super easy. All we got to do is crunch some numbers.
Okay.
I'm going to be super lazy here. One thing I notice is that this is in microcoulombs, that's in microcoulombs, that's in microcoulombs, that's in microcoulombs. If all the Q's are times 10 to the minus 6, if I just multiply everything by 10 to the positive 6, all that will cancel. So I don't have to convert units. It's probably funny, my computer report crashes. There's so many technical problems today. This is crazy. It's Monday. I'm off my game.
Okay.
Right.
It's been a long week.
It's been a very long week.
Weekend. Let's say. People are going crazy.
Yep, it's nuts. All right, so in this problem, we have, I need negative b, but b is 0.4 times q2. And what was q2? Q2 was 10, right?
Negative 10.
Yes, but remember that what we're doing is we're doing the magnitudes.
Okay.
So we're never going to put a minus sign in there. The minus sign we already took care of by putting that there.
Okay.
So we'll just use 10. So it'll be negative b, so negative 0.4 times 10 plus or minus the square root of b squared, which is 10, no, sorry, 0.4, 0.4 times 10 squared minus 4 times a. But what is a? A is
6.
Q2
No,
minus Q1.
wouldn't it be 60?
No, it's, all right, you remember Q2 is 10,
Oh,
Q1 is 50. So it's 10 minus 50 is negative 40.
negative 40, yeah.
And then what is C? 0.04 times Q2. So 0.04 times Q2, which is 10. All over 2 times A. So that's 2 times negative 40.
It's all over the 2 times A.
Yep.
That's negative 40.
So 0.4 times 10, so that's negative 4 plus or minus the square root of, and then 10 times 0.4 is 4 squared minus is plus, so plus 4 times 40 times 10 times 0.04 is 0.4 over negative 80 on the bottom.
Huh? Whoa.
I just did the math. That's all I did.
So 4 times negative 40. Made it a pot. Okay. 0.4 over negative 80. Square root.
So the thing under the radical is 80, right? So the square root ends up being 8.94. And so I have two possible answers. 8.94 minus 4 divided by negative 80. That's going to give me a negative value for R2. But that's stupid because R2 is a distance. It can't be negative. That's dumb. So I ignore that one. The other one is negative 4 minus 8.94. Well, that's going to be negative 12.94 divided by negative 80.
You said that 8.94 was negative as well?
Well, remember, the formula has a plus or a minus, right?
Mm-hmm.
So in principle, the solution to this problem could have two possible answers. One of them is if it's negative 4 minus 8.94, I have negative 12.94 divided by 80.
Mm-hmm. So it's two answers.
Well, sort of. Quadratics always have two solutions.
Okay, so that is that. So
Right? So this is one solution. The other solution, though, would be negative 4 plus 8.94. That's 4.94 over negative 80. Which is negative 0.06175. Right? Except, remember, what are we solving for? We're solving for distance. What does negative 0.0675 meters even mean in this picture?
it's going to the left. The left.
So if I go to the left, I'd be over here, but we already know this won't work. So the negative answer is stupid. And we throw it out. This is the answer. And so that tells me that from here to here needs to be 16.1 centimeters. And at that point, the two things are equal. Super easy. Now notice it only works on this side because in order for this to work, I have to be further away from the 50 and closer to the 10. It won't work over here because here I'm closer to the 50 and far away from the 10. That doesn't work. I get a stupid answer. So the only solution is right there. Does that make sense?
Yes.
Okay. Super easy. Let's make it more complicated.
No.
You know I'm gonna. All right. Let's look at that exact same problem, but now I'm going to look at the electric field someplace else. So 50. And actually, let's make it easier. I'll take that back. Let's go positive 50, negative 50. And place them 20 centimeters apart. But this time, rather than look at any place along that line, I'm going to look at the electric field at a third location. Go halfway in the middle and then up 10 centimeters. And I want to look at the electric field right there. If I wanted to calculate that electric field, I'd do the same process we've been doing. I'd find the electric field for this guy, the electric field for this guy, and I'd add them together. So far, so good?
Mm-hmm.
So, what direction is the electric field going to be from the positive charge at that location?
So wait. So you asked me what would be the direction on point B from point A?
Well, so I'm looking at the electric field at this location right here. And I got to think about it for both of them. I'm going to do it one at a time. So first, I'll think about the electric field that's caused at this location by just this one. Ignore this guy.
Yes.
And only think about this guy. What direction is its electric field going to be?
Its electric field to the left.
What's the rule?
Opposites attract things.
So for finding the direction of the electric field, the rule is you imagine putting a positive charge at this location, and you ask yourself, what direction would this positive charge, this imaginary positive charge, be pushed by this charge over here?
Down.
Why would it be down? So if I put a positive charge there, it would be repelled from this charge here because they're both positive, right? So it would be pushed diagonally up and to the right. I'm going to call that E plus because it's the E from this charge here.
Okay.
Electric fields always point away from positives and toward negatives.
Okay. So how do you get the diagonal though? Like,
well, because from here to there is diagonal.
okay.
If it had been over here, then I would have gone straight to the right. So it's always along the line connecting the charge who's making the force and the imaginary positive charge that's feeling the force.
Okay.
And I'll do that same trick for this guy. His electric field is going to point, since he's a negative charge, it's going to point towards it. So it's going to point along that line.
Okay.
So you can see why this is more complicated than the previous ones, is because in each of the previous examples, all of my electric fields, even if they were in different directions, they were along the same straight line, right? And if all the vectors are along the same straight line, when you add them together, it's just like straight math, right? They're either both to the right, so they're both positive, or one is positive, the other is negative. But here, my two vectors, they're not even along the same straight line, and I have to add them together. So how do you add vectors that are not collinear?
How do you add vectors that aren't collinear?
Yep, that are not collinear.
And that means what? Straight?
Collinear means along the same line. Co meaning together, linear meaning line. Same together, the line together. Great words. Math guys love them.
I don't, I'm lost for words.
So it's a thing that you guys have been doing in this class since Physics 1. You add vectors, and the way you do it is first, you break those vectors down into X and Y components, so that when you do that, all the I hat parts are collinear with all the other I hat parts. So you add all the X parts together.
Yeah.
J hats are collinear with the other J hats, so you add those together. So by splitting them up into X and Y components, you can just do regular math on the components.
Yeah.
So that's what we got to do. We got to find both of these electric fields. Then we're going to break them down into I hat and J hat components.
Okay.
And then we'll add them up.
Okay.
So far, so good?
Yes.
Okay. So first, before we can do any of that, let's figure out, like, how big is this vector? How big is E plus? So we'll find the magnitude first, then we'll split that magnitude into components. So for E plus, it's going to be K times Q over R squared. That's the magnitude, right? So K is 8.99 times 10 to the positive ninth. Q is 50 times 10 to the negative 6. What is R?
I want to say 0.1, but it may be 0.5.
Nope, neither of those.
Neither. Do
Roscoe, stay back. Nope, stay back. Stay back. Stay back. Right. Leave it. So look, R is this distance right here. Now, I know from here to here is 20 centimeters, which means from here to here was 10. From here to here is 10. So I've got a right triangle, because that right there is a right angle. And it's 10 on this side, 10 on this side. So this is the hypotenuse of an isosceles triangle. So it's going to be a squared plus b squared equals c squared. So c, if you will, is going to be equal to the square root of 10 squared plus 10 squared. That's 100 plus 100, so 200. The square root of 200 is like 14 and change. So 14.14 centimeters, or 0.1414 meters. And that is this distance here, which is R.
Okay.
So I get a whopping 2.25, we'll call it, times 10 to the 7th newtons per coulomb. And that's the magnitude of E plus. You buy that?
Yes, give me 1 second, just doing the calculations in my calculator.
Yep.
You say you are. You got, yeah, I got that.
Okay. Now, the good news for us is when I go to do the electric field for the negative charge, it's going to be the same size Q, the same distances. It's going to be the same number. So E minus is the same number. That's super easy.
Okay.
So all I've got to do is break that down into components. So for E plus, it's diagonal, right? I'm going to draw it off to the side here. Here's E plus, and it's up and to the right. That's going to be a little bit sideways. That's the X component. A little bit up. That's the Y component. And it's making some kind of angle that I don't know. I need to know what that angle is. What angle would that be? Well, if I wanted to figure out this angle here, one thing I noticed is that since this is along this same line, this angle right here is the same as that angle right there.
Yeah.
And if I wanted to find this angle right here, I could use this right triangle right there. If I wanted to find that angle, the tangent of that angle should be opposite over adjacent. So if I go tan theta equals opposite, that's 10, divided by adjacent, that's also 10. Well, that's just 1, right? Which means theta should equal the inverse tangent of 1. And what's the inverse tangent of 1?
45.
45 degrees. So because this was an isosceles triangle, that happens to be a 45-degree angle. So now when I go to break E plus into components, what's going to happen is E plus in vector component form is going to be this times the cosine of 45 in the I hat direction, plus that same thing times the sine of 45 in the j hat direction. With me there?
Yes.
How's the electric field for the negative charge going to be different?
It's going to be negative 2.25 times 10 to the 7 cosine. Everything's going to become negative.
Nope.
No?
Nope. Look at the picture. So E plus points up and to the right.
But E negative E points down
And to the right.
to the right.
So they're both to the right.
So does it stay positive?
Does what stay positive?
The equation? No. Something has to become negative.
Something becomes negative, yes. What is it that becomes negative?
The X direction.
No, the X direction is positive because they're both to the right. Remember, the x direction is left and right. The y direction is
The
up and
y
down.
direction to go down.
So what's going to happen is they're both going to have a positive x component.
Mm-hmm.
It's the y components that are going to be different signs. So for E negative, it's going to be positive 2.25 times 10 to the 7th cosine 45 I hat. The I hat components are exactly the same. It's this part.
Mm-hmm.
That's opposite. Now, when I go to add them together and get my total, what's going to happen is their J hat components are equal but opposite. Those cancel. I'm going to have this twice. So 2 times 2.25 times 10 to the 7th cosine 45. It's all in the x direction, nothing in the y direction, which means my final answer is straight to the right. No up and down components at all. So now,
I got 3.18
that's exactly correct.
to the right. Yeah. Mm-hmm.
Piece of cake.
Yeah, sure.
That's it. That's all there is to it.
You know me and words, though. Me, words, and equations be a lot.
All right, so I'm going to go ahead and call it a day. We'll come back tomorrow. We'll learn about electric field lines, and that should finish off chapter 18 in its entirety.
Okay. When
Next
will
time, I remember to hit the
the
record button at the beginning of class so I don't have to do the Cliff Notes super fast version.
right. When is the lab? When are we to start the lab, or when is it due?
Well, you should start the lab last Friday.
Okay.
It is due this Friday.
Okay.
Yeah, labs are always going to be due on Fridays. We'll meet well, I'm usually recording them Friday mornings. It's supposed to be at 8, but I think I did it at 9 because nobody's going to be here at 8 anyway.
Okay. So we have lab on Fridays.
We do. Like if you were you around last semester, or you already dropped at that point?
I had dropped it after
Yeah.
like test one.
Okay. Yeah. So you weren't around for the online version that we did in the spring. But what we did there is we met for a lab during the lab time, and people used breakout groups to work together so that they weren't like off on their own.
Yeah.
If you're around when I'm recording, you're more than welcome to work with whoever's around then, and I'll be there to answer questions.
Okay.
But yeah, it'll be like 9 a.m. on Fridays.
Okay.
We'll do those, and if you can't be there for that, it's no big deal. I'll record the thing like I did last week and just post it.
Okay.
And I'm always here for emails. So.
Yes, sir.
All right. Well, I will see you tomorrow.
Okay. See you tomorrow.
Yes, ma'am.
Bye bye. Have a good day.
You too.